Okay, now it is recording, and we're starting only 7 minutes late. So,
It's okay. You went over last
yay,
time.
attendance.
But we also have Friday
I-
Thursday off.
Yeah, I went 1 minute over. So. Okay.
You cover more material than most.
So I've been told, yes, which actually is kind of scary because, like, to me that just means that other people are not covering enough.
Some people like to tell stories in the middle of their lectures.
I had no idea.
It's on camera.
Okay. So. All right, so we will make a brief foray into Chapter 11, just to only cover this one section of it, because we started the semester solving systems of linear equations, and we just spent some time on solving a single nonlinear equation. So what happens when you put the two together? You have this, systems of nonlinear equations, and we're going to use ideas from both topics, really, to solve these kinds of problems. And really, the reason I'm covering this section, because I don't really feel like it, but it's not. You're gonna have this from your teacher, even if it's a class you like. You come to a topic and like, what are we supposed to cover today? You look at what it is, and it's like, oh, that. So that's my current mood. So, yeah, and worse, I budgeted 2 days for this section, so we'll see how it goes. But like I'm looking forward to what comes next, and that's differential equations, and that's actually why we need this. At the very end of a semester, we'll we'll solve differential equations by solving systems of nonlinear equations, and then we'll need this stuff for it. Okay, so the problem I need to describe precisely is if you are given a continuous function f, but before it was just a function of a single variable, y equals f of x. Not anymore. So this is a function that's defined on an n-dimensional domain that I'm calling D, which could be the whole n-dimensional space, for all we know. And its output is also n-dimensional space. So this is a vector valued function, which is why I have the vector symbol. So, and you could think of this, one term is given to this as a vector field, because its input is a vector and its output is a vector of the same length. So given such a function, our goal is to find some vector now x, which would have components x1, x2, up to xn, in the domain of a function D, such that big F of vector x is the zero vector. So it's a problem we've been talking about, except generalized to n dimensions. So instead of having one equation in one variable, we have n equations in n variables. Okay. Now, before I could even talk about this, I need to set some notation. Let's see, where do I have an example of this? Wow. And here I'm looking at my own book. It's already been edited. It's like, wow. I wrote this section crappily. What was I thinking?
I don't like this topic.
Well, that too, but yeah. So No, because I was thinking, I know I have an example of this kind of problem. It was just a little later in the section than it should be. So that's an example in the case where n is equal to 2, so two equations and two unknowns. The equations would be, or actually, f of x1 and x2 would be a vector consisting of two components. So that would be x2 minus x1 squared for the first component, and the other component would be x1 squared plus x2 squared minus 1. So we want to find where this function is equal to 0. Now if you want, you can think of x1 as just plain old x, and then x2 would be play the role of y. I didn't do that here just because I want to keep it the same notation as having components x1, x2, x3 for however many I have. Now, let's see. So, if I want to solve the equation f of x equals 0, can be described as solving these equations. So I have these set equal to 0, but what I can do is rearrange them. x2 is x1 squared, and then x1 squared plus x2 squared is equal to 1. So all I've done is I've moved selected terms over to the right side. No big deal. Now, so what I could do is I could graph these equations. So like instead of all points x1, x2 that satisfy this equation, that's one curve, and then this equation is another curve. And where these curves intersect, that's when you have x1 and x2 that satisfy both equations, and then you'd have a solution to the entire system. So if I were to graph these, and remember, you can think of this as x and this is y. So what kind of curve is this? Yeah, it's a parabola. It's y equals x squared. Everyone's favorite parabola, presumably. And here's a badly drawn parabola. So this is x2 is x1 squared. All right, and what about the other one? Circle. Yeah, that's just a unit circle. So I'll give you a badly drawn circle. A little better, maybe. Not really. So this is x1 squared plus x2 squared equal 1. And we can see where they intersect. And they have two intersections. This one here in the first quadrant, and this one in the second quadrant. Now, you can see from this example, though, that it would have been very easy to change this example in such a way there'd be no solution whatsoever. Like if I had written x2 is equal to x1 squared plus 2, so it would shift the parabola up by 2 units, there'd be no intersection. So in general, we cannot assume that a function big F is going to have any roots whatsoever. But if not knowing for sure whether it is or not, we'll try our best to find one. And by using the methods that we've seen in Chapter 10, well, not bisection. Bisection won't help us here, but like fixed point iteration, Newton's method, a variation of the secant method. We'll try to adapt those to this n-dimensional setting to be able to solve these kinds of systems. Okay. Now, So actually, the first kind of method that I'm going to take from chapter 10 to describe how it can be generalized to solve this kind of equation is fixed point iteration. So what I need to do is a quick recap of that. Okay. I think I covered this. I covered this before spring break. Loads of time for you to forget it all. All right. So this was section 10.3. So what you do in this case is you rewrite your equation f of x equals 0 in this form, x equals g of x. So then the algorithm is that you guess some iterate x naught that you hope will be close to a solution. And then your actual iteration, you set xk plus 1 is equal to g of xk. And you keep iterating until either it converges or you see that there's no hope of convergence. And what will be important to us here is to refresh your memory on when does this work? When is there a solution? So a solution exists if a function g maps some interval ab into itself. In other words, for any x in AB, g of x is also in AB. So we'll have a similar existence condition for the multi-dimensional case. And as far as the condition that's actually about uniqueness and ensuring that fixed point iteration will converge, if the absolute value of g prime of x is less than or equal to some constant L, which is less than 1, on some interval AB, then we can say that not only is there a fixed point, but it is unique, and the iteration is guaranteed to converge. For any initial guess in this interval. And we've seen that if this condition of a derivative being bounded in this way is, like if derivative is greater than 1 in absolute value at the fixed point, then the fixed point iteration will generally fail. So we need that derivative to be small. Hopefully this at least rings a bell. So now I'm going to describe fixed point iteration for a function of n variables. So for a system of equations, whoops. All right. So what we do, like before, is we rewrite in some way as x equals some vector valued function g of x. And what I'll do in a little bit is I'll revisit this example that we have, these two equations, and show like how we could rewrite that and different ways, because just like with fixed point iteration for one variable, if we rewrite as x equals g of x in the wrong way, the derivative will be too large and won't converge. So the same problem will happen here. So we somehow algebraically, using dang it. Okay, I'll bring it. Whoever's watching this like, what? Okay. Yeah, so for strange person glasses 1 to strange person glasses 2. All right. So then, like before, we have some initial guess, which will now be a vector. X naught. So the algorithm is going to be exactly the same. All right, so if I write these as steps, we rewrite, we guess, and then we carry out our iteration. We get each new iterate by substituting the old iterate into G. Okay. Until convergence. And how you would measure convergence in this case, your iterates are now vectors. So that would mean that you would take the difference, xk plus 1 minus xk, and now you would use a norm. Now we talked about norms quite a while ago when talking about iterative methods. So it's the magnitude of a vector. So for instance, it could be the largest element, which is the infinity norm. Or it could be the 2 norm, which is square root of sum of squares. For our purposes, it doesn't really matter which. And if one vector norm is small, they're all going to be small. Okay. So you choose some vector norm here, and you want that to be less than some sort of error tolerance. You said that you would set, like maybe it's less than 10 to the minus 8, something like that. So you just keep in mind that we're measuring magnitude differently now. It's no longer its absolute value. It's a vector norm. Okay. So this is the method. And now before I talk about, I'll talk about existence. The exact condition is exactly the same. Existence of a fixed point. If your function g maps some domain D, well, I don't want to call it that, because I'm already using that, R, within Rn. So for instance, it could be some rectangle, for instance, into itself. So any vector x you plug that's in this domain R already, you plug it into G, and it's still in that domain, then a fixed point or solution exists somewhere in this domain R. Okay. So it's the exact same existence condition as in one dimension, where we require G to map an interval into itself. Same idea. That glare there. Ugh. Yeah.
So just as a recap on the convergence norm, that has to be a natural norm, and it can't be some other odd type of norm, like a Frobenius norm.
You're thinking of matrix norms, because matrix norms are natural norms induced by a vector norm.
Mm-hmm.
But here we're just dealing with a vector norm.
Okay, so it doesn't matter if it's a
Not yet.
Not yet.
We will need matrix norms in a little bit. Okay. So we'll work with this one. And attempt fixed point iteration. So to solve this system that I don't feel like writing out again. By fixed point iteration. What we need to do is write these equations in a certain form, x equals g of x, which means we need to have two equations where on the left side we have x1 or x2. So we have either of these components isolated on one side, and it has to be a different one each time. So we're going to have these two equations written that way. So what I can do is, so our attempt, not knowing if this is going to work or not, I'm going to take the second equation and isolate the one from a circle and isolate x1. So x1 is equal to the square root of 1 minus x2 squared. And then for the second equation, where x2 is isolated, I'll just use the first equation over there. So x2 is equal to x1 squared. So this system of equations is equivalent to the original, because all it does is rewrite one of the equations, and then but it's now in the form x equals g of x. So g of x, which is g of x1 and x2, is equal to these right sides. All right, so now we'd like to see if there's some domain that we can choose where G maps this domain into itself, so we can know that there is a solution in that domain. So I'm going to let R, my domain R, be just the a square in the first quadrant. So x1 and x2 are between 0 and 1. Now, what you can do is, if you assume that x1 and x2 are between 0 and 1, you can actually see, without too much trouble, that the values, the g values, if I plug the numbers in here between 0 and 1, the results will also be between 0 and 1. Because if I take a number between 0 and 1 and square it, that'll be between 0 and 1. And if I subtract such a number from 1, that'll also be between 0 and 1. Taking the square root will keep it between 0 and 1. I'm assuming the positive square root here. So I can say that the function g maps R into itself. So any point in this square, g maps into another point in that square. So therefore I can conclude g at least has a fixed point within this square. And actually we can see that from the picture over here. This point is within that square that I'm outlining like crazy here. So we see from the graph that a solution exists. So now we just have to try using fixed point iteration to find it. Now, so what I'm going to do is enlist MATLAB to help me. I'm going to pick an initial guess. So I'll just pick an initial guess in the middle of the square. I'll pick a point 1/2, 1/2 for both components. So what I need to do is substitute this into my function g, take a result of that, substitute that into g, and so forth, and we'll see what happens. We'll see if it converges to a solution. Okay. Well, actually, can y'all even see this? Okay. All right.
If I have any questions, I'll ask.
Okay.
I can see it right now.
Okay. I'll use a big font.
Bigger.
I don't want to carry out too many iterations anyway. All right. So the first iterate is 1/2, 1/2. So I'll just do a few iterations, like up to 5. So I need to quickly code up this function in MATLAB. Okay, and actually what I'll do is, after I make my MATLAB statement, I will write that on the board. So I want it to be this function right here. So it would be square root of 1 minus x2 squared. And I'm making it a column vector, so then x1 squared. Okay, so my MATLAB statement to define my function g is g is equal to @ x1, x2, and I use square brackets to make a column vector. So I do square root of 1 minus x2 squared, semicolon to make it a column vector, and then the other component is x1 up arrow squared. Close the column vector. So that defines my function g in MATLAB. And now I can set my initial guess to be a column vector, 1/2, 1/2. So I'll go ahead and do that. Okay. And then I can start my iteration. I can say x is equal to g of x. So this is what I'm literally doing at the prompt. So here's my prompt. And I just keep doing that and see what happens. So if you have your laptop open, you can try it along with me. Okay. All right. So if I do.
Well, you have G
Not
equals,
me,
what's the very first thing?
Of this,
G equals.
g equals @. And then in
That is not what I say. Where's your A? It looks like the swirly thing from
That's back.
Atlantis.
That is backwards. If you flip it that way.
oh, you mean like
An actual
I thought it was
Like-
a
Do the A
swirl.
like that?
No.
A.
Do A and then you go around.
It's swirly. There's no other swirly character in the ASCII set. What other thing are you going to think it's going to be?
I mean,
Greek letters is
I thought
right
it
up
was from
there.
Atlantis, the movie.
No,
Cartoon.
that definitely looks great.
Okay, I'm looking at the mat sign here as a sample.
Do an A, a little A, and then the tail goes around it.
Okay.
And then there you go.
Right.
That's an
Okay.
at sign.
Yes.
Okay.
I just did like some weird loop-de thing because I was like, sure.
Yeah, it's like, it's never come up before. Okay, I need to. All right. Sorry for those of you watching about my @ sign and about not seeing the whole statement.
It's okay, they were curious too. They don't know it yet, but they were.
All right. So actually, like, okay, so it doesn't look like an @ sign. I'll admit that.
Not.
What else could it be?
Oh, we didn't know. That's what she asked.
I'm not going to make up characters.
At some point, someone
I know
did.
this is. I know
At
this is.
some point, someone did, which is.
I
why
know
we
this is a
have
math
loop
class,
de.
but still. Okay. Well, that was surreal. All right. Well. Okay. So now if I go ahead and do this statement, that's a lot more readable. X equals g of x. What?
Legible?
Readable's a word.
Readable?
Yeah, it is.
Readable?
I like that word. Don't let her get you down.
Readable?
Oh. Ah, dang it. I messed up. No, okay. Well, I guess I'll just erase this statement anyway. No, here's why. Reason why this doesn't work is x is a vector, a single empty, but the way I wrote this function is a function of two arguments. In other words, I had to make the components separate. And the thing is, if I were to use it like this, I'd have to say g of x of 1, x of 2, which is kind of cumbersome. So what I really should do is just correct this, which is actually not hard to do, thankfully. So it has to take a single, I don't have to change my at sign anyway. The at sign's the only thing that stays. Let's take a single argument x, and then I have to refer to the components of x in here. So, in other words, I don't have enough room, but I'd say x parentheses 2 squared to take the second component of x there. And then here, also, x parentheses 1 to get the first component of x. So otherwise, the formulas will stay the same. Okay, so I didn't trash my statement completely, but now it should work. Okay, so it's a good thing that people watching could not see the first statement because it was wrong anyway. Okay, so now I'll correct that here. I hope none of my Stanford peeps are watching. They'd be so ashamed of me. Okay. Actually, one of my, when I was at UC Irvine, mostly teaching calculus, one of my colleagues in the department, according to one of my students, made a mistake in class, just like this, and was asked about it, and he simply refused to acknowledge that there was a mistake. Like, no. Okay. Don't do that. Okay, so now I have my initial guess all ready to go. So I try x equals g of x, and please work this time. Yes, it works. Okay, so my new iterate, I'll write these as decimals. It'll be 0.86. I'm just going to do 2 decimal places. So really be 0.87, 0.25. Okay. And then if I keep doing this, so now x is overwritten with the new value. So now I just do this statement again. So that's literally what I'm doing at the prompt, is just repeating this statement. And I get, so x2 be 0.97, 0.75, kind of bouncing around. Okay, and then 0.66, 0.94. Seems to not really know where it wants to go. Well, I'm in agreement there. 0.35, 0.44. So it's being kind of psychotic. And then 0.9 and 0.12. So if I were to draw these, yeah, it'd be like all helter-skelter of a graph. So I was hoping that 5 iterations would at least give us an idea as to what the outcome will be. So what I'm going to do off screen is keep going, and that's actually really freaky.
It just keeps bouncing.
Yeah, and you're doing it now? Yeah, so, okay, what I'm finding is it goes to the corners of the square, and it keeps going around the corners. So think about it, suppose that x1 and x2 are both equal to 0. Then I would get 1, 0, a different corner. Suppose they're both equal to 1, I get 0, 1. So again, it takes a corner to a different corner. So these first iterates, it's trying to find its way to one of the corners, and eventually it will get to one, and then it just stays locked into that. So now that's pretty much what I have. That's what it's doing. It's rotating among all the corners. In other words, doesn't converge. So this iteration failed. Okay. So now that we see that it's failing, we'd like to have some idea as to, well, first of all, why, and second, and second, what can be done about it? Now, we saw this coming up with regular fixed point iteration for one equation, where we had a bad g, so then we would rewrite it, and like the example I had, x equal to minus natural log of x, and hopefully get convergence that way. Okay, now, so what I'm going to do is I need to state a condition for convergence, like with because of a fixed point iteration with one variable, this is the condition that we had. The derivative had to be bounded away from one, like so strictly less than one in absolute value. So what is the appropriate condition in this case, now that we have several variables? Because the whole notion of just a plain old derivative needs to be adjusted for this case. But to do that, I need to find some notation. And some of you might recognize this from multivariable calculus, which a couple of you were in that. So you've got plenty of time to forget. So the Jacobian Matrix.
It's just like what?
I've triggered you, haven't I? So the Jacobian matrix of a function g.
N equals 0.
What?
Wrong class. Sorry.
That's n variables to n variables.
Yeah.
Is written this way. So use a big old J. If whatever function I have, whatever function I'm taking the Jacobian of is a subscript. So this is an n by n matrix. And G, since it has a vector valued function, it has component functions. Actually, I should write this as G of x. Is g1 of x, g2 of x, gn of x. Okay. So in this example, we have those two component functions. However many you have. So what you do is you take all the partial derivatives, all the first partial derivatives of all the component functions. So first row would be partial derivatives of g1 with respect to all the different x's. And this always comes up when I teach multivariable calculus. These are not 2's. That's a 2. Those indicate partial derivatives. Similar to like df dx, but we can't use a d because we're in multivariable land now. And then the second row would be all the partial derivatives of g2, the second component function. And so on, all the way down to the end. So partial derivatives of gn with respect to x1, x2, up to xn. Now, in our situation, the number of input and output variables are the same. But you don't have to be. So you could have a rectangular Jacobian matrix. We just don't need that now. So it's not all, it doesn't have to be square. Okay, so instead of having just one function that's a derivative, like g prime of x, now we have this n by n matrix of partial derivatives. So what we can say is at fixed point iteration, converges if some norm, matrix norm, so now we're dealing with matrix norms, of a Jacobian is less than or equal to some constant. In the book I call it rho, not sure why I did. But it's the same idea as the constant L, the Lipschitz constant from single variable case. Less than 1. Now I should emphasize this is sufficient for convergence. Also, on our domain R. Is sufficient, not necessary. Okay. We can also think in terms of the spectral radius. We would want to have a spectral radius be less than 1, certainly at the fixed point itself, and also near it. Otherwise, convergence is not likely to happen. So it's similar to iterative methods, Jacobi, Gauss-Seidel, SOR. If the norm of the iteration matrix is less than 1 for most iterative methods, we have convergence. And in fact, I'm going to make a connection between fixed point iteration and those iterative methods. Okay. Okay. So, so these are stationary iterative methods. Actually, I never really talked about the non-stationary ones. For AX equals B, well, they can be written this way. XK plus 1 is equal to M inverse N XK plus M inverse B. And we needed, so this is our iteration matrix, which I called T. We needed that to have a spectral radius less than 1. And if it had a norm less than 1, then we would have convergence. Well, if I call this whole thing g of xk, so there's a function of xk that produces xk plus 1, then the Jacobian of g is M inverse N. And sure enough, if it has spectral radius 1, then it converges. Now, the easiest way for you to see why this is the Jacobian of this is you think in terms of ordinary nice functions of a single variable. If I have a function like this, f of x is equal to like 3x, what's my derivative? 3. All right. So if you have a linear function of any number of variables, it can be written this way as a matrix times your vector x. So it's like basically you're multiplying by a constant. It's just here it's a constant matrix instead of a constant number. So the Jacobian of this linear function is the constant matrix that's multiplying it. Just like here, the derivative is the constant. It's the exact same idea. Instead of like carrying out painful partial differentiation with respect to all these variables, you can just understand it that way. So So just as we need a norm or a spectral radius less than 1 here, we'd like to have the same thing in this situation for fixed point iteration. It's just that now the Jacobian matrix is not constant because it's a nonlinear system of equations. It can be a function of x1, x2, etc. Okay. So now we have at least a sufficient condition for convergence. So now what we'll do is go back to our example and take a look at that g, and we'll actually look at the partial derivatives and see how they behave. Okay. All right. Well, should have a vector sign on it. Okay. So now I need to take a partial derivatives of these functions with respect to x1 and x2. So Jacobian of g all right. So, well, for the first entry, I take the derivative with respect to x1. There is no x1 in here, so it's going to be 0. Take a derivative with respect to x2. So that will give me 1/2, 1 minus x2 squared to the minus 1/2 times minus 2x2, which I can simplify some. And then derivative of this with respect to x1 is 2x1. And then the derivative with respect to x2 would be 0. So that's my Jacobian matrix for this example. And what we can see here is, if we take a look at this, 2x1. Well, x1 could be between 0 and 1, so this could be as large as 2. So the norm, I can just look at the infinity norm, which is the largest row sum, is not less than 1. On our square that we're working with. So not necessarily a deal breaker, but it certainly appears to be in this case. So with that in mind, it's not surprising that it failed. Okay, so what we can do is let's consider an alternative. If we go back to these equations, we need to isolate x1 and x2 to get a g, but let's isolate them differently. All right. So if I go back to these equations, instead of having x2 is equal to x1 squared, that's setting the stage for a derivative that's going to be too large. So what I'll do is, our new g, I'll take this equation and instead of isolating x2, I'm going to isolate x1. So x1 is equal to the square root of x2. It's always a good idea to invert these relationships, like we did with regular fixed point iteration, because if a derivative or partial derivative is greater than 1, then you take the inverse function, and now you take a reciprocal of that derivative, thus making it small. And then I can take this equation, and I can solve for x2. So x2 is the square root of 1 minus x1 squared. And we can see if that is going to work any better. Now, so what I'm going to do is I'm going to change my MATLAB statement up here to work with these functions. Okay, so g is going to be square root of x2, and then the second component will be square root of 1 minus x1 squared. Okay. and then I'll set my x, my initial guess to be 1/2 like before. So now I will try this iteration. Actually, what I'll do is, with the new g, just for fun, I'll write the iterates just to see if we can observe anything different this time around. I haven't done it in the book, so I honestly don't remember how this goes. Well, I know the final outcome. Okay, so our first iterate is 0.71. I'll just do 2 decimal places, 0.87. But then we'll see if it acts psychotic again. 0.93, 0.71. Okay, and then 0.84, 0.37. That's a little discouraging. Okay. 0.61, 0.54, and 0.74, 0.8. Okay. Not quite as schizophrenic. But if I were to keep going, then we're mostly staying in the upper quarter of that square. And as I keep going, they're slowly stabilizing. In fact, yep, I'm getting convergence. So roughly like 0.79 and 0.62. But it just takes a while. So if I look at the Jacobian matrix this time, all right, so with respect to x1 would be 0. Okay, the diagonal entries are 0. This would be 1/2 x2 to the minus 1/2. And then this would be similar to the other one, it would be minus x1 over the square root of 1 minus x1 squared. Okay, now the thing is, actually, I'm going to rewrite that as a square root. 1 over 2 square root of x2. So, if x2 is greater than 1/2, then that will be less than 1. The other component, the other non-zero component, let's see, if x1 is greater than 1/2, it's kind of iffy, but I think that'll turn out to be less than 1 in that case too. But what I can say is that the spectral radius of Jacobian is less than 1 near a fixed point. And that will lead to convergence, at least if your initial guess is close enough. So it's not an ideal G by any means, it's just a better one than before, because it's not driving the iterates to the corners. So we are getting convergence, it's just quite slow, unfortunately. So in fact, if I look at the eigenvalues, well, what I'm going to do is I'm going to make the Jacobian matrix in MATLAB using these x values that I currently have. So 1 over 2 square root of x2, and then minus x1 over square root of 1 minus x1 squared. Okay, and then if I look at the eigenvalues, so it turns out the spectral radius is roughly 0.9 near the fixed point. So that explains two things. One, why we're getting convergence at all, because at least it's less than 1. Also seeing why the convergence is slow, because it's close to 1. We'd really like to have it smaller than that. Because, like, for one variable, really butt-slow method like bisection, errors cut by half. And that's not really good. So we'd like to have an asymptotic error constant smaller than 1/2 for such methods. Yeah.
How do you enter in the Jacobian matrix into MATLAB?
Oh, so what I did here was, so I did like square bracket 0, and then for x2 I would have x parentheses 2. And I already have an x defined because I've been doing the iteration.
Oh, you can. Okay.
Yeah,
so
I'm not doing it as a function.
You can say. Okay. Yes.
Yeah. Yeah, so all I'm getting is a Jacobian matrix at a certain point.
Okay.
Yeah. So, okay. So, actually, what I'm going to do here is I'm going to let x1 and x2 vary between 0 and 1. I'm going to pick a bunch of them. Okay. So now I have points scattered throughout the square R. And, oh, actually, that's going to be a big pain. What I wanted to do was actually be able to plot the spectral radius of a Jacobian on the entire square. Except to work, I had to work with a different matrix at each point. Okay, I'm not going to do that. So it would take too much time. I may do it later, and so I can show you guys the results, but not something you do during class. You'll all be sitting here like, what is he doing? So, okay. Well, okay, you're doing it anyway. I want to be completely honest. So, okay. All right. Okay. So, well, you know what? That is all I have on fixed point iteration. Okay. Yeah, I'm done because I'll use Tuesday to cover
You have to stay to make up for the time that you were late.
Newton's method. Okay, so all right. Since I went 1 minute over last time, I'm giving you 10 minutes back. Yeah. Okay. So I'll continue Newton's method for systems on Tuesday.
Make that happen.
Yep.
I got cardboard to steal.